So at this point, we've already talked a little bit about how to evaluate certain kinds of logarithms, like this one where we have log base 2 of 8. If we use the general log rule to convert this to an exponential function, we'll go ahead and set this equal to x because that's the value we're trying to find, and we'll convert it and say 2 to the x is equal to 8. And we can just eyeball the fact that 2 to the third power is going to be equal to 8, and so we can say x is equal to 3. So we know how to solve basic logarithmic expressions like that one. But sometimes things are going to get a little bit more complicated and difficult, and so we'll have to do a little bit more algebra to figure out the value of this unknown, wherever the unknown happens to be. So for instance, sometimes we're going to have the case where the base of the logarithm is greater than the argument. So in this logarithm, and all the ones we've looked at so far, the base is less than the argument. Here the base is 2, the argument is 8, 2 is less than 8. But in this one, the base is 27, the argument is 3, and so the base is greater than the argument. We're still going to want to fall back on our general log rule and convert this to an exponential function. When we do that, we'll get 27 to the x is equal to 3. And now this looks a little bit more difficult because it doesn't follow this same pattern of just, oh, I can raise 2 to the third power and that gives me 8. What do I raise 27 to in order to get 3? Well, the answer is that the exponent is actually going to be a fraction. But the easiest way to solve an equation like this one is to try to get the bases equal to one another on both sides. So over here on the right-hand side, we have 3. We could think about this as 3 to the first power. If we can get the expression on the left to have a base of 3, then we can set the exponents equal to each other. So here's what that looks like. 27, we know, is actually 3 to the third power, because 3 to the third, so 3 to the third, is 3 times 3 times 3, or 3 times 3 is 9, 9 times 3 is 27. So 3 to the third is 27. So we can actually rewrite 27 as 3 to the third. We want to go ahead and put it in parentheses just to keep everything clean here. So we'll replace the 27 with 3 to the third. We still have the exponent of x, and then we get 3 to the 1 over here on the right. Now here's where we have to go back to exponent rules. We're going to need to apply power rule for exponents to the left-hand side here, which tells us that when we have one exponent raised to another, so we have 3 to the third to the x, we can multiply those exponents together. So 3 to the third to the x is the same thing as 3 to the 3 times x, or 3 to the 3x. So we can rewrite this as 3 to the 3x is equal to 3 to the 1. Now we have the bases equal to each other on both sides. The base of the left-hand side is 3, the base of the right-hand side is 3. When that's the case, the only possible way this equation can be true is if the exponents are also equal. And that should make sense to us because if I, for example, say 3 to the 1 is equal to 3 to the 2, I know that this isn't true. 3 to the 1 is 3, 3 to the 2 is 9, 3 does not equal 9, so this is not true. So when my bases are the same, my exponents can't be different and this still be a true equation. So since my bases are equal to each other here, that means the exponents have to be equal. So 3x has to be equal to 1. So I can say 3x equals 1. So I can simply divide both sides of this by 3 and get a value here of x is equal to 1/3. What I've just found is the value of log base 27 of 3. So when I'm given this expression, log base 27 of 3, I go through this process to determine that the value of this is 1/3. And what that tells me is that I have to raise 27 to the 1/3 power in order to get 3. So that's an example of how to solve a log when the base is greater than the argument. You're also going to have a situation where the argument is a fraction. So in this case, we have log base 8 of 1 over 512. So 1 over 512, the fraction, is the argument of the logarithm. And we want to solve for the value of this. We want to figure out what the value is of this log expression. And what we're really asking here is, what do we have to raise 8 to in order to get the value 1 over 512. So again, we'll go ahead and convert that to exponential form using the general log rule, and we'll say 8 to the x is equal to 1 over 512. We're going to try to solve this problem in the same way that we solved this first one over here. What we want to recognize is that 512 is the same as 8 to the third. If I have 8 to the third power, that's equal to 8 times 8 times 8. 8 times 8 is 64. 64 times 8 is 512. So 512 is 8 to the third. So I can rewrite this expression here as 8 to the x is equal to 1 over 8 to the third. Again, I'm going to bring in an exponent rule. In the same way that over here with this expression, we brought in the power rule for exponents, here I want to apply the negative exponent rule, which tells me that when I have an exponent inside of a fraction here, I have 8 to the third and that expression is inside of a fraction. If I want to move that term with the exponent from the denominator to the numerator or the numerator to the denominator, I can do it, I just have to change the sign on the exponent. So if I want to move 8 to the third up to the numerator, all I have to do is make the exponent of positive 3 a negative 3. So 1 over 8 to the third is actually the same thing as 8 to the negative 3, just moving that up to the numerator. And now you can see that I have 8 to the x is equal to 8 to the negative 3. And again, this is only true if the exponents are equal to one another because the bases are equal to each other. So I can simply say x is equal to negative 3. And what is this value, negative 3, that I found? That's the value of this logarithmic expression, log base 8 of 1 over 512. That is equal to negative 3. So those are a couple of specific cases. Here where the base is greater than the argument, here the argument is a fraction. But in general, what we're doing, no matter what kind of log expression we have, we're trying to equalize bases. Here in this first problem, we equalized the bases on the left and right hand side by making both of them equal to 3. Here we made both of them equal to 8, and that allowed us to set exponents equal to each other. So this is a process that you can fall back on to solve lots of different kinds of log problems, and it's something you always want to look for. If we go through one more example here, we'll see what that looks like. So again, converting this log equation into exponential form, we say that 32 raised to the x over 5 power is equal to 64. The goal here is to solve this equation for x. So you'll be given sometimes equations like this one and asked to solve for the variable. All you're going to do is try to equalize bases the same way we did over here. So I have 32 raised to the x over 5th power is equal to 64. What I want to notice is that both 32 and 64 are powers of 2. 32 is actually 2 to the 5th power. So I want to rewrite 32 as 2 to the 5th. So I'll say 2 to the 5th raised to the x over 5 is equal to 64 is 2 to the 6th power. So I can say 2 to the 6th power for 64. Now I go back to my first example. I'm going to apply power rule for exponents and multiply 5 by x over 5. So this is the same as 2 raised to the 5 times x over 5, which is equal to 2 to the 6th. When I multiply 5 by x over 5, I get the 5's to cancel with one another, and I'm simply left with 2 to the x is equal to 2 to the 6th. The bases are equal. I have a base of 2 and a base of 2, which means the exponents have to be equal, so I can say x equals 6. So with x equals 6, I've solved this logarithmic equation, and I can say log base 32 of 64 is actually equal to 6 over 5. And so this equalizing bases technique is one more method you can use to solve all different kinds of log problems.